In Chapter 13, we'll be learning about types of studies, in particular experiments versus observational studies. To start, an observational study is exactly what it sounds like. Researchers are simply observing the patients, and they're not attempting to affect them in any way. There's three main types of observational studies. There's retrospective studies. These study past data. When you think retro, think old. There's prospective study. This goes into the future. And then there's cross-sectional studies, which study data from a specific point in time. One key thing to note is anytime we're dealing with observational studies, they're useful for discovering trends or associations in between two variables, but we can't ever determine that there's a causal relationship between two variables. In other words, we can't say from an observational study that an explanatory variable is the cause of any changes in a response variable. If we're interested in making that kind of causal determination, we need to conduct a randomized comparative experiment. Now, the difference between an experiment and an observational study is that an experiment involves some kind of treatment. And that treatment is applied randomly to a certain number of the subjects. And once that treatment's applied, we monitor the subjects and we see how it affects some kind of response variable across different groups. This will allow us to prove that cause and effect. We want to identify at least one explanatory variable called a factor. We're going to manipulate that factor. We identify that as the treatment, and then we're measuring a response variable, which hopefully we'll see changes in as we manipulate that treatment or factor. Here's some terminology we want to be familiar with before moving forward. When we're conducting an experiment, the things that are receiving the treatments are called experimental units. If the things receiving the treatment are people, we usually refer to them as subjects or participants because it's a little more socially acceptable than to call them experimental units. I mentioned on the previous slide that we have a factor which we're manipulating. The number of ways that we can manipulate that factor are called the levels of the factor. I also mentioned a treatment a few times at this point, and the treatment is actually the combination of all the different factors that we have in an experiment and the ways that they can be put together. Go ahead and pause the video at this point, read this example problem, and see if you can identify the key components in this problem as requested in items A through D. Now, this is an example on your notes page as well for you to follow along. So in part A, it's asking you to identify the experimental units. Keep in mind, experimental units are what in the experiment is receiving the treatment. So in this example, 15 plots of land are receiving this treatment. So those are experimental units. Part B, identify the factor. Okay, the thing that we're manipulating is the type of fertilizer. The number of levels is 3 because we have 3 different types of fertilizer. The number of treatments is just the combination of all the different factors and all the different levels. It's easy when we just have one factor, okay, because that makes it the number of levels we have. One factor at 3 levels means there's 3 treatments. Lastly, part D, the response variable is what we're measuring. And in this case, we're measuring the mean yield from the plots. Anytime we're asked to design an experiment, there's 4 main things that we want to address. The first is control. When we talk about control, we're talking about controlling outside sources of variation. So in this case, what we mean by that is we want to attempt to minimize any external sources of variation that might affect our response variable. Let's go back to that previous example about testing different fertilizers on 15 plots of land. In that case, external sources of variation might be how much the plots of land are water, pests, sunlight. To minimize those, we want to make sure that all 15 plots of land are getting watered the same amount, they're getting the same amount of sunlight. If they're being treated for pest control, that they all get that same type of treatment. We want to try to make sure that the only differences in those 15 plots of land is our factor. So when it comes to the end of the experiment, any differences we see in the response variable can be attributed to what fertilizer they received. Next, we have the key concept of this entire unit, which is randomization. Now, on the previous slide, I mentioned 3 things which might affect our experiment, which are water, sunlight, and pests. All of those might affect the crop yield of these 15 plots of land. Now, admittedly, there's other things that maybe I'm not thinking of. Okay, so just as one example, perhaps that different plots of land have different nutrients in the soil, and maybe they're grouped together. So if I were to just assign the 5 first plots to the first fertilizer, the next 5 to the next fertilizer, and the last 5 to the third fertilizer, we'd be grouping them together, and they might benefit or be hindered by whatever nutrients are in the soil. Okay, randomizing our plots of land and which treatments they get would effectively equalize that. All right, it neutralizes out unknown or uncontrollable sources of variation. Third, we want to include replication. We're doing this experiment with 15 plots of land, so we can assign 5 plots to each of the 3 fertilizers. Obviously, the more plots we have, the better, and any differences we see in the response variable, in the mean yields of crops, gets more convincing with the more data we have, with the more plots of land we have. Lastly, this is not an essential component of experimental design, but it's always something we want to consider including. It's called blocking, and this is similar to stratifying with sampling. And really the only difference is we stratify with samples, we block in experiments. So let's say in our 15 plots of land, half of them were shaded by a forest and the other half had full sun. Okay, we would start off by separating the two groups, and then we would randomly assign treatments to the 2 groups. Okay, when we were talking about stratifying, I would often go to the example of males and females as what we would stratify on. Blocking is quite the same, right? So a lot of times we would block on gender. Okay, so we would separate males and females into 2 groups, and then we would randomly assign treatments within each of those 2 groups. So we run our experiment, we get our mean crop yields, and they're going to be different. Variation is natural. We expect them to be different. They would be different even if the fertilizer had absolutely no effect on how well those crops grew. What we really want to know is, are these differences statistically significant? And we're going to spend a lot of time on what this phrase actually means in the coming chapters, but for now the key thing to realize is differences are statistically significant if they're larger than what we'd expect to see just from chance alone. Now, the first principle of experimental design was control, and that was about minimizing external sources of variation, so the only differences in our response variable can be attributed to the factor that we're manipulating. A lot of times the way that we'll do this is by having a control treatment, which we'll refer to as a control group. Now, a control group often is a group that receives no treatment. Referring it back to the example we've been using, maybe 5 of the plots receive no fertilizer at all. That would be one of the treatments. Okay, that would allow us to compare any growth in the other 2 plots to a baseline and see how well they grew compared to a plant that receives absolutely no fertilizer. Control groups don't have to receive no treatment. They can receive a treatment that just produces a known result. Like if the farmer has used the same fertilizer for a long time and knows how well the plots or how well the crops grow using that fertilizer, that could serve as the control group as well. It's not unusual to have people involved with an experiment that have some kind of psychological investment in seeing the experiment succeed. In this case, we have a farmer who wants to see some kind of difference between the different plots because that means he's found a fertilizer that increases his crop yield, which would in turn increase his profits. That desire for success might affect the results even subconsciously as he starts to measure the results at the end of the experiment. And for that reason, we might want to include blinding in this experiment. Now, blinding is when we keep the examiner of the subjects in the dark about what treatments were received. Okay, so in this case, the farmer would be kept in the dark. He wouldn't be told which plots received which treatment. Now, there's another level of blinding, and that's blinding the subjects being treated. We can't really do that in this experiment because the subjects being treated are plots of land, and obviously a tomato plant is going to be unaware of which fertilizer it's received. Okay, but just keep in mind there are 2 ways to blind an experiment. If just one of those 2 groups is blinded, either the subjects or the person evaluating, okay, it would be called a single blind experiment. If both groups are blinded, it's called a double-blind experiment. Also keep in mind, someone has to know which plots are assigned to which treatments so we can actually evaluate the yields effectively once the experiment comes to an end. So let's talk about an experiment where the subjects are people, which is pretty much the case in any experiment where we're testing medication. Now this leads us to an effect which is called the placebo effect. And the placebo effect is a psychological effect where our mind kind of tricks us into thinking we're being treated when we're actually not. For example, let's say you have a headache. I give you an M&M. I say, take this M&M, you're going to feel better. Right? You eat it. It's really just a piece of candy. But psychologically, you've been given some kind of medicine, or at least you believe, and your mind tricks you into thinking you're going to feel better. And you do feel better. Okay, it's a fake treatment. That's what a placebo is. Okay, and you report that you feel better because you've been given some kind of treatment. Okay, placebo is a way to blind subjects. So anytime we do a study or an experiment with medicine, we'll have two different treatments. They'll look exactly the same. Ideally, they'll taste, smell, they'll be identical to one another, with the only difference being that one is an actual medicine and one is a placebo, a fake treatment with no actually medicinal qualities. We'll randomly assign them to two groups, and then we'll measure the differences between the two groups. Hopefully in Unit 2 we remember lurking variables. This is when we were dealing with scatter plots and we had two variables. We plotted them on an XY coordinate plane. And then there was another variable that we weren't really aware of that was affecting both of them at the same time. It was creating an association between the two, and it kind of implied that one was causing the other. With experiments, there's something similar. It's called confounding. And when two variables are confounded, it means they're both being affected at the same time. Really, there's two factors at play. They're both affecting our response variable, and we can't separate the effects of one factor from the other. So let's say we have our 15 plots of land. I'm going to draw them out in our sketch here. And let's say we didn't randomize our treatments, okay, which we would never actually do because that's pretty much the biggest mistake we can make. But we put all of our first treatment in that first row, second treatment in the second row, third treatment in the third row. And then let's say off to the right of all these plots of land is a big forest. Those are my beautiful trees there. And then the sun rises over off to this side here. All right, so as the sun rises and shines on all these plots of land, we could see that these would get full shade here. All right, these would get partial shade. It's going to look like full shade, but you guys get the idea. And then the first row, row 1, would get full sun. Okay, so if at the end of the experiment we saw that the fertilizer in row 1, treatment 1, seemed to grow the best, treatment 2 seemed to grow second best, and treatment 3 grew the worst, is that because those fertilizers actually were the most effective, or is it because those first couple plots got the most sun and those third plots got the least sun? We're not sure. Our experiment's been confounded. The way we deal with this is by randomization. If we randomly assign our treatments, that pretty much equalizes out all these external sources of variation, and we don't have to worry about confounding. Last concept for the main example is matching. Now, when we're incorporating matching into an experiment, we're making our subjects as similar as possible and we're pairing them up. For example, let's say we're studying the effect of music education on grades. So we want to take one student who studied music and one student who hasn't. If we're using matching, we want these students to be as similar as possible. And we want them to be similar in ways not understudied. Okay, so the only difference is their music education, which would allow us to eventually look at the response variable, which is their grades. So by matching them, we would pair someone who has studied music with someone of the same sex, same family income, same age, etc., but hasn't studied music. All right, this is our main example for the chapter. Read through this example, pause the video, and then go ahead and fill out on your notes those 4 questions about experimental units, explanatory value, etc. You can stop when you get to number 5. The experimental units are the 8 tanks holding the salmon. We could also say that they're the salmon within those tanks. Those are the things that are receiving these treatments. The explanatory variable is the fish food. There's 2 levels of this food, the old and the new. Since there's 1 factor at 2 levels, there's 2 treatments. The response variable is the average weight gain of the salmon by tank. It's important that we include the word average in there because we are taking the mean weight gain across all these salmon. Number 4 asks how we would implement blocking within the experiment. And the thing we need to pick up on is that in the text of the question, it references a considerable temperature gradient within this room that holds the 8 tanks. So when we look at this diagram, we see a few different sources that would affect the temperature of these tanks, namely this door in the front, the heater in the back of the room, and these 2 windows. So let's say we were to block pairs of tanks together. We would want to group each 2 tanks with respect to their temperature to create pairs of tanks that would have the most similar temperatures. So 2 obvious tanks would be tanks 2 and 3 due to their proximity to the door. Additionally, 6 and 7 are close to the heater. They would likely have similar temperatures. 1 and 4 are both near windows in the corners. And our last block would be 5 and 8 due to their proximity both to the heater and those rear corners. Let's summarize the problem up to this point. There's a new fish food on the market for salmon, and we want to compare it to the old food to see which is more effective in increasing the weight of salmon. We have 6 months to run the experiment in a room containing 8 tanks and a considerable temperature gradient. So the first thing we did is we grouped the tanks by which were most similar in terms of their temperature. Now, we haven't talked about it yet, but once we have our blocks, so we have a block of, say, 2 and 3, we have to randomly assign treatments to tanks. Randomization has been a very key concept in this entire unit, and we continue with it in this chapter. So we have our 2 tanks by the door. Those were chosen because they're close to the door and we expect them to have similar temperatures. So we want to randomly decide which gets the old food, which gets the new food. We can use our graphing calculator. We can use a random number table. For something like this, we could also just flip a coin because there's 2 options. So let's say we flip a coin. If we get heads, we'll assign the new food to the lower number tank. If we get tails, we'll assign the old food to the lower number tank. And we'll do that for every block. So we'll assign those blocks. It's also important that we measure the weight of the salmon at the start of the experiment and then again at the end of the experiment. And then finally, we'll compare the average weight gains across all these different blocks. So here's a diagram of our design. We start off with our 8 salmon tanks and we block them. Okay, we have tank 1 and 4, 2 and 3, 5 and 8, 6 and 7. Okay, here we can see we're randomly assigning which of the 2 treatments our tanks are getting. So within each block, we have treatment 1 and treatment 2, the old and the new. Those are being assigned randomly by flipping a coin. At the end of 6 months, we're going to reweigh the salmon, which were weighed initially. We're going to take the averages of each of these tanks, and we're going to analyze the average differences in weight gains for the old treatments and the new treatments, for old food and new food. So finally, as our last step, we have to put this into words. Okay, and here's how we would write it out. Tanks within the room have been blocked according to their expected temperature due to their proximity to windows, the door, the heater, etc. Randomly assign treatments within each block by flipping a coin. Again, as always, it's key to describe how you're randomly assigning these treatments. Heads will result in the lower number tank being assigned the old food, while tails will result in it being assigned the new food. The higher number tank will get the opposite food. At both the beginning and the end of the 6 months, record the salmon's weights. This is explaining how we're going to measure our response variable. For each block, analyze the gain by subtracting new food minus old food and seeing if the average across all blocks is significantly different than 0.